Today, we're diving into the secret material that honestly makes up almost everything around us. I mean, look around you. From the clothes you're wearing to the phone in your hand, we are living in a world built from polymers. But what exactly are they?
Okay, let's start with a little riddle. What do a plastic water bottle, a car tire, and a nylon jacket all have in common? They seem totally different, right? Well, the answer is they're all polymers. And that incredible diversity is exactly what makes them so fascinating and, frankly, so essential to modern life.
So to really understand what makes a polymer, we have to start small. I'm talking microscopic level small, with the fundamental building blocks.
At its heart, a polymer is just a gigantic, long-chain molecule. The name itself kind of gives it away, right? It's from the Greek words poly for many and mer for part, so many parts. Imagine a string of beads that's thousands, maybe even millions of beads long. That's basically a polymer.
And you guessed it, if the polymer is the whole string of beads, then the monomer is the single individual bead. It's the one repeating unit that connects over and over and over again to build that massive molecule. If you can wrap your head around this one little piece, you've got the key to the whole thing.
So how do you actually go from a bunch of loose beads to a full-on chain? Well, one of the most common ways is a process called addition polymerization. It's basically a chemical chain reaction in 3 simple steps. First, something has to kick things off. That's called initiation. Then, boom, monomers start adding on like crazy, one after another. And finally, termination. The reaction stops and you're left with a brand new super long polymer molecule.
But here's where it gets really interesting. It's not just about having a long chain. The real secret sauce is how these chains are arranged. Their molecular architecture is what determines if a polymer is stretchy like a rubber band or tough enough to stop a bullet.
The simplest structure is linear. I want you to think of uncooked spaghetti, just long, individual strands that can kind of slide past each other pretty easily. This ability to move around is a really key characteristic, and we're going to come back to it in a second.
Next up, you've got branched polymers. So here you have that main spaghetti strand, but now it's got smaller side branches sticking off of it. And as you can imagine, those branches get in the way. They get tangled up, making it harder for the chains to pack together or slide around. This tangling totally changes the material's properties.
And finally, we have the most rigid, most locked-in structure, cross-linked. In this case, those spaghetti strands aren't just tangled. They are chemically bonded together. We're talking strong bonds. So instead of separate chains, you get one single massive interconnected network. If linear polymers are spaghetti, this is like a baked lasagna, where everything is held together in a grid. It's not going anywhere.
Okay, so these 3 structures, linear, branched, and cross-linked, they aren't just some abstract chemistry concept. They directly create the 3 main families of polymers that we use every single day.
And that difference in structure has huge consequences. Take thermoplastics. Their linear chains can slide around, which means you can melt them down and reshape them over and over. That's why they're so easy to recycle. But thermosets? Totally different story. Their cross-link structure is locked in for good. If you heat them up, they don't melt, they just burn. That chemical reaction is irreversible.
Then you have the third family, the elastomers, which is a fancy word for what we all call rubbers. And these guys are special. They're famous for their incredible ability to stretch out to, like, many times their original size, and then snap right back into shape.
So what gives them this stretchy superpower? Well, it all comes down to a really clever twist in their architecture. See, elastomers are cross-linked, just like thermosets, but only lightly. These loose connections act like tiny molecular springs. They let the chains stretch way out when you pull on them, but then they pull everything right back into place once you let go. It's an absolutely brilliant piece of molecular engineering.
All right, I'm going to throw a number at you. 70%. Any ideas what this represents in the world of polymers? I'll give you a hint. Think about all the plastic stuff you use every single day.
Did you guess it? That 70% is the market share of thermoplastics. Their ability to be easily melted, molded, and recycled just makes them incredibly versatile and cheap to manufacture, and that is why they absolutely dominate the polymer world. And this brings us to the central theme, the big takeaway from all of this. It turns out the very molecular structure that gives a polymer its best properties also creates its biggest limitations. It's a paradox that's built right into the material itself.
I mean, on the one hand, Polymers are total wonder materials. They're lightweight, they're cheap, they don't rust or corrode, they're fantastic insulators and have an amazing strength-to-weight ratio. It's really no surprise they've replaced heavier materials like metal and glass in so many products.
But, and there's always a but, right? Here's the other side of that paradox. Compared to metals, most polymers just aren't as strong or as stiff. They can't handle really high temperatures, and some of them even break down if you leave them out in the sun for too long. These are the built-in trade-offs that engineers are always trying to solve.
So, if there's one thing you take away from this, let it be this. A polymer's entire identity, its strength, its flexibility, its recyclability, everything, is decided at the molecular level. That invisible arrangement of chains dictates everything we see and touch in our real world.
And that leaves us with a final, pretty cool question to think about. If a polymer's microscopic architecture is both its superpower and its Achilles heel, what's next? What will the next generation of polymers, designed from the molecule up to overcome these trade-offs, even look like? That's the question that's driving the whole future of materials science.